So inductance of a single phase dual line, just now I showed you the diagram, right. So it is a that is your, so this is the two conductors carrying current I1 and I2 equal, but in opposite direction, because one entering into the page, this plus symbol, and dot means it is leaving the page, right. So this current set up magnetic field lines, these are shows magnetic field lines between the conductors as shown in this figure 3, right. So inductance of conductor 1, right, when this conductor, right, due to internal flux is given by equation 21, that we have seen half into your 10 to the power minus 7 Henry per meter, right. So as a simplifying assumption, we can assume that all the external flux set up by current in conductor 1, right, links all the current up to the center of conductor 2. That means we are making an assumption that we can assume that all the external flux set up by current, when this external flux set up by this current, right, it your what you call by current in conductor 1, this one we call conductor 1, right, links all the current up to the center of the conductor 2. That means if we make the flux line up to the center of this conductor 2, not beyond that, only up to the center of this conductor, not beyond that, and this is quite your fair assumption, right. So similarly for similarly under the flux beyond the center of conductor 2 does not link any current. This is our assumption. That means whatever this conductor 1 carrying current I, so external flux only we assume it links up to the current up to the center of the second conductor 2, but not beyond that. This we are making an assumption, right, and it does not link any current. This assumption gives quite accurate result when D is much greater than R1 and R2, right. That means the distance, this distance D is much greater than R1, this radius of this conductor is R1 and this radius is R2, right. So thus to obtain the inductance of conductor 1 due to the external flux linkage, substituting D1 is equal to R1 and D2 is equal to D in equation 26, that means this equation, that means in this equation I told you, no, from this we can make out. So in this equation 26, in equation 26 what we are doing is that we are substituting D1 is equal to R, D1 is equal to R and D2 is equal to D in equation 26. So directly we are substituting in this equation D1R and D2 is equal to your D. So that's why you will get L1 external, you will get that 2 into 10 to the power minus 7 ln D upon R1 Henry per meter. This is your equation 27, right. Therefore the total inductance of conductor 1 is then given by L1 is equal to L internal inductance, we have got it half into 10 to the minus 7 plus L1 external means this one, right. So this is the total inductance of the conductor 1, right. That means you substitute L1 is equal to half 10 to the power minus 7 plus 2 into 10 to the power minus 7 ln D upon R1, right. You take from this 2, you take 2 into 10 to the power minus 7 common. If you do so, this term will become 1 by 4 plus ln D upon R1. This 2 common, so it will be 1 by 4 ln D upon R1, right. Now is equal to 2 into 10 to the power minus 7, you write ln, so this 1 by 4 you can write e to the power 1 by 4, right. So this you can write 1 upon 4, because ultimately it will be 1 upon 4, ln e is actually 1 because log of e base e, right. So it is 1, so that's why we can write ln e to the power 1 by 4. So is equal to, we can write ln is equal to 2 into the power minus 7 ln D upon R1 e to the power minus 1 upon 4 Henry per meter. It is something like this, it is something like this, it is in the bracket term, it is ln e to the power 1 by 4 plus ln D upon R1 is equal to ln D e to the power 1 by 4 by R1 is equal to ln D, this e to the power 4 you bring in denominator, it will become it will be r e to the power minus 1 by 4, right. So, that is why this term we have written 2 into the power minus 7 ln d upon r1 into e to the power minus 1 by 4 Henry per meter, or this one you convert to a natural log to common log, right, and convert it to, it is Henry per meter. So, convert it to milli Henry per kilometer. This is a small exercise for you, you do it, right. When you listening this lecture, you please do it, right. So, it is taken instead of natural log, we have taken the log. So, if you substitute, if you convert it, and remember Henry you have to convert it to milli Henry, and meter you have to convert it to kilometer. So, it will become actually 0.4605 log d upon r1 dash, right. R1 dash is given here milli Henry per kilometer, right, where r1 dash is equal to r1 into e to the power minus 1 upon 4, that is equal to 0.7788 r1, right. So, this r1 dash actually called fictitious radius of the conductor, right. So, that means this is a standard formula for this, to say, to find out the inductance, right. So, 0.4605 log, this is for single conductor. Now, this radius r1 is the radius of the fictitious conductor actually, which has, we assume, which has no internal inductance, right. This way you can imagine, but has the same total inductance of the actual conductor, that is the meaning of that 0.7788 r, the fictitious radius of the conductor, right. Similarly, the inductance of conductor 2 you can find out. So, it is same thing, L2 is equal to 0.4605 log d will be there, but radius of the conductor was r2. So, it is r2 dash milli Henry per kilometer, and r2 dash also same thing is equal to 0.7788 into your r2, if r1 r2 both radius are different, right. So, r2 dash is equal to 0.7788 r2, it is milli Henry per kilometer, right. This is equation 30. Therefore, the total inductance of the circuit, because one is current going, another return path, right. So, total inductance is called loop inductance, right. So, total inductance of the circuit is L is equal to L1 plus L2, right. So, 0.4605 log d upon r1 dash plus 0.4605 log d upon r2 dash, right. Therefore, L is equal to 0.4605 log, then both you make it d square upon r1 dash into r2 dash is equal to 0.4605 log d upon under root r1 dash r2 dash whole square. This 2 will come here. So, it is 0.4605 into 2 log d upon under root r1 dash r2 dash, right. So, 2 into 0.4605 is equal to 0.921 log d upon under root r1 dash into r2 dash milli Henry per kilometer. So, this is that total, this is that inductance of the your complete inductance, this is called loop inductance, and this is the formula of that your what you call that total inductance of a circuit, right. So, this is equation 31, this is milli Henry per kilometer, right. Therefore, if the two conductors are identical, that means we assume r1 dash is equal to r2 dash is equal to r dash, that means your what you call that means your I mean r1 is equal to r2 is equal to r, right. That means your r1 dash is equal to r2 dash is equal to r dash. We are assuming the radius is r, r1 is equal to r2 is equal to r, right. Therefore, r1 dash is equal to r2 dash is equal to r dash. So, r dash is equal to 0.7788 into r, fictitious radius of the conductor, right. Therefore, L will become 0.921 log d upon r dash milli Henry per kilometer. This is equation 32, right. So, now equation 32 gives the inductance of a two wire line in which one conductor acts as a return conductor for the other. This is known as loop inductance, right, because you are considering the complete circuit, right, one incoming, another outgoing. So, totally this is called loop inductance, right. So, this now from equation 29, that means this equation. Now from equation 29, that means this equation, right, this equation 29, the inductance of conductor 1 can be written as, it is given 0.4605 log d upon r1 dash millihenry per kilometer. What you do, this equation you write 0.4605 log 1 upon, we are assuming here that r1 is equal to r2 is equal to r dash. So instead of r1 here writing directly r dash, understandable, right, there should not be any confusion. So 0.4605 log 1 upon r dash plus second term 0.4605 log d upon 1 upon r dash, but we are putting 1 because of some reason, right. So here at 1 upon r dash is okay, plus 0.4605 log d upon 1 millihenry per kilometer. This is equation 33. So this equation we put in this form, because our objective is to find out some generalized formula, right. Therefore similarly for the conductor 2, right, this is equation 34. Similarly the inductance of conductor 2, right, same we can write L2 is equal to 0.4605 log 1 upon r dash plus 0.4605 log d upon 1 millihenry per kilometer. This is equation 34. As both the conductors are identical, hence we can write L1 is equal to L2 is equal to L, they are same. Therefore inductance per phase per kilometer length of the line is given by L is equal to 0.4605 log, now we are writing in general, therefore the inductance per phase per kilometer length of the line is given by, we are writing that L is equal to 0.4605 log 1 upon r dash plus 0.4605 log d upon 1 millihenry per kilometer. This is equation 35, right, because we are writing L1 is equal to L2L. Now from this equation 35, it is clear that first term is only a function of the fixed TCS radius of the conductor, this term is only function of r dash, and second term is only function of d, right. So first term here it can be that equation 35, that means this term can be defined as the inductance due to both internal flux and that external to conductor 1 to a radius your 1 meter, right. That means this term, first term, can be defined as the inductance due to both the internal flux and that external to the conductor to a radius up to 1 meter only, that is why 1 upon r dash, right. Similarly the second term of equation 35, right, that means this term, second term of equation 35, right, is dependent only upon the conductor spacing, because between the conductor distance is d, the conductor spacing, and this is known as inductance spacing factor, right. So this is the two terminology, right. So this term is called inductance spacing factor. Later from this one we will see some generalized thing, right. Now next thing will come that self and mutual inductance, right. Suppose you have single phase 2 wire line viewed as two magnetically coupled coils, you assume they are magnetically coupled, right. So current is one case, this is the dot convention is taken, right, as currently entering the dot, so taking that is a plus, if leaving the dot it is minus, but in this case both dot are taken here, right. So one is incoming, another is outgoing path. So I1 actually I1 is equal to minus I2, but direction is taken like this, and they are entering into that dot, and self inductance of this conductor 1, it is L11, self inductance of conductor 2 is L22, and mutual inductance between them is M12 is equal to M21, right. So this is the single phase 2 wire lines viewed as two magnetically coupled coils, right. Therefore the inductance per phase for the single phase 2 wire line, that is figure 3, just hold on, figure 3 I will show you again, just hold on. This is your this is your figure 3, this is your figure 3, right. So, this circuit also we are taking as a magnetically coupled circuit, right, representation is like this is actually your figure 3, right. So, can also be expressed in terms of self inductance of each conductor and their mutual inductances, the way it has been represented here, right. Later figure 4 is marked later, right. So, let us consider the single phase circuit represented by two coils characterized by the self inductances L11 and L22 and the mutual inductance M2, I mean this one, this one, right. So, that is why figure 4, this is that figure 4, right, shows the single phase line views as two magnetically coupled coils and the magnetic polarity is shown by dot symbol. The flux linkage lambda 1 and lambda 2 can be written as that dots current entering the dots will take the positive one, right. So, flux linkage 1 lambda 1 lambda 2, you can write lambda 1 is equal to L11 I1 plus M12 I2, right, M12 and this is due to the current I2. So, M12 I2, this is equation 36. Similarly, lambda 2 for this one is equal to M21 I1, M12 is equal to M21, but we have to write from the mathematical point of view M21 I1 plus L22 I2, right. This is equation 37. This plus here also plus sign, here also plus sign, because current both the cases we assume entering into the dot, right. Now, but current one is incoming, another is outgoing, but I2 is equal to minus I1. So, if you put I2 is equal to minus I1, we will get both the equation you put I2 is equal to, one equation you put I2 is equal to minus I1, another equation will put I1 is equal to minus I2, right. If you put, you will get lambda 1 is equal to L11 minus M12 bracket close into I1, this is equation 38. Similarly, lambda 2 is equal to minus M21 plus L22 bracket close into I2, this is 39, right. Therefore, we can write L1 is equal to L11 minus M12, I mean this is your L1, and L2 is equal to minus M21 plus L22, this is your L2, this is equation 40, this is equation 41, right. Therefore, you compare equation 40 and 41 with equation 33 and 34, just hold on, I will bring equation 33 and 34, just hold on. Yes. So, this equation 40 you compare with equation 33, right. So, if you compare it with equation your equation 40 with 33, so this is equation your 33, right. So, what one can do is, I am putting it here, look, just hold on. This equation 33, it is written like this, I am rewriting equation 33, I am rewriting equation 33, right. So, in this case your L1 is equal to 0.4605 log 1 upon r dash plus 0.4605 log d upon 1, right. This one you can write L1 is equal to 0.4605 log 1 upon r dash, so minus 0.4605 log, I am writing instead of d by 1, it is minus is taken here, so 1 upon d. This is actually your equation 33. Now, we are comparing this equation 33 with your equation 40. This is now equation 33, and next if I put equation 40, that is L1 is equal to my L11 minus M12, right. So, when you comparing these two equation 40 and 41, just hold on, where it has gone, this thing. So, when we are comparing, actually L11 is equal to this one, that your L11 is equal to your 40 and 33 we are comparing, right. So, L11 is equal to, just I am writing 0.4605 log 1 upon r dash, right, and M12, this is here, it is L11 minus M12, already minus sign is here. So, M12 is equal to 0.4605 your log 1 upon d. So, if this is just we are comparing this, just we are comparing these two, that is why when you similarly for L2, L22 also both are same, when you compare 41 and 34 it will remain same. Therefore, L11 is equal to L22, actually this is 0.4605 log 1 upon r dash millihenry per kilometer, this is equation 42, and M12 and M21 same 0.4605 log 1 upon d millihenry per kilometer. So, this was d by 1, taking minus here making log 1 upon d. So, this is actually L11 and this is actually M12. So, this is that this is just the same thing, right, how we can go for this comparison, right. So, hold on. So, now this is whatever we have seen for two conductors, right, one is going and the other is incoming. Now, if you have say n number of conductors, right, and that is this above described approach of self and mutual inductances can be extended to a group of conductors, right. Suppose let us consider n conductors carrying phasor currents I1, I2, In and so on, right. So, you have a group of conductors, n number of conductors, and we can make it I1 plus I2 plus dot 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 up to plus In is equal to 0. This is equation 44, right. So, generalized formula for the flux linkage of conductor I is given by lambda I is equal to LII, capital LII plus j is equal to 1 to n, j not is equal to I, Mij Ij. This is equation 45, right. Look, here we have written only for two conductors, L11 is 1, L1 is equal to L11 minus M12, this is for one. If you add another one more term will be added and so on. So, that is why this instead of this is your and that is why this your this lambda 1, right, lambda 1 is equal to basically L11 I1 minus M12 I1, but the sign minus sign will come because of this direction of the current Ij. So, in general this lambda 1 is, instead of lambda 1 we can write for ith conductor lambda I is equal to LII, capital L suffix II into II plus j is equal to 1 to n Mij into Ij and j not is equal to I. This is the generalized formula for the flux linkage of conductor I. So, only from this simple thing, small thing, we are giving this generalized formula. This formula will be used again and again for other things. So, this is this mathematical expression for flux linkage for conductor I is very important, right. So, this is actually equation 45. So, if it is so, hold on. Therefore, if you have this one, therefore, from that we have seen lambda 1 your what you call that lambda 0.4605 this thing common all the time, right. So, in this case what we have seen is that lambda I can be written as 0.4605, take common, II into log 1 upon Ri dash, same formula you are using, plus Ij log 1 upon Dij, j is equal to 1 to n, j not is equal to I, milliweber turns per kilometer. So, there we have seen two terms, this is this one, there you have seen first term is 1 upon r dash, second term is 0.4605 log 1 upon d, and this is 0.4605 log, this is the first term, this is the second term, the mutual term, right. So, in this case, in this case, So, this mutual term we are writing the same one we are writing, it was given 1 upon d. So, general thing you make j is equal to 1 to n I j log 1 upon d I j, j is equal j not is equal to I, and first term 0.4605 will be common, first term I log 1 upon R I dash, right. So, this flux linkage formula will be used again and again, right, your what you call for your calculating the flux linkages of other configuration. Now, there is a figure here, actually I checked carefully, this figure I have taken from a book, right, but this figure is actually incorrect. So, we will correct it, right, the how many conductors will be there around, this particularly the first, second, third layer, this counting is not matching. So, this figure you should not do it, I will tell you how to do it, right. So, figure 5. So, next is type of conductors. So, transmission line conductors used in practice are always stranded, right, to provide the necessary flexibility, and stranded conductors are also known as composite conductors, right, as they compose of 2 or more elements or strand electrically in parallel. So, this configuration I will give you the formula, this how many conductors were. So, outsider one where totally white one, it is aluminum strand, and inside that it is steel strands, right. This is steel strand, the shaded one, and other one this aluminum strands, just to increase the mechanical strength we will give that, right. So, the conductor used for transmission line are stranded copper conductors, hollow copper conductors, and aluminum conductor steel reinforced, that is ACSR, that is we call aluminum conductor steel reinforced, right. In overhead transmission lines, ACSR conductor is most commonly used, right. You will see that ACSR conductor. The low tensile strength of aluminum conductors is made up by providing central strand of high tensile strength is steel, right. So, the central strands, these are actually steel, right, these are actually steel strands, right. So, ACSR conductors have the few advantages, I have written few such that I should not miss anything, right. It is cheaper than the copper conductors of equal resistance, coronal losses are reduced because of the larger diameter of the conductor, right. So, this is second point, and third point is it has superior mechanical strength and hence span of larger lengths, which result in smaller number of supports for a particular length of transmission line. That is mechanical strength is or this thing what you call your superior, very strong, then the span between the two towers can be increased such the number of towers will be less, right. So, that is why it has superior mechanical strength, because it is steel strand centrally, right. So, the total number of strands in bracket S in a concentrically stranded conductor with total annular space filled with strands of uniform diameter d is given by, there is a formula that y is the your what you call number of layers, there is a formula S is equal to 3y square minus 3y plus 1, right. That means, this one, this formula if you say this one S is equal to 3y square minus 3y plus 1. For the first one, when y is equal to 1, you substitute y1, you will get S is equal to 1. When y is equal to 2, you will get substitute 2 square 4, 12 minus 6 plus 1, it is 7, 1 plus 6. Then when y is equal to 3, then S is equal to your 3 into 3 9, 27 minus 9, 18 plus 1 19. So, 1 plus 6 plus 12 is equal to 19. So, when y is equal to 4, then S is equal to, I think it will be 1 plus 6 plus 12 plus 18 is equal to 37. That means, in this diagram, actually when y is equal to 1, first is central one 1. When y is equal to 2, 1 plus 6 7, so second layer it will be 6 conductors, right. When y is equal to 3, third layer there will be 12 conductors, 1 plus 6 plus 12, 1 6 12, here counting 12 not coming. So, this diagram is incorrect. So, around this there will be 12 conductors, right. And next one, if you go for the fourth one, then there will be 18 conductors, and last one here 1 2 3 4 layer is there. So, total will be, last layer will be 18 conductors, but total will be 37. So, right. So, you can make it of your own, right. So, that is the thing. So, this diagram, this is our counting, it was I think some less than 12, it is not correct one, right. So, some drawing error is there. So, that means, and the total diameter it is given d dash is equal to 2y minus 1. If y is equal to 1, then d dash is equal to d. If y is equal to 2, then d dash will be 3d, and so on. So, this is the overall diameter of the standard conductor. D dash is equal to 2y minus 1 into d. This is equation 48.